In this lecture, we're going to review the first of a number of different statistical procedures referred to as the one sample z-test. And we begin with a review of a z-score. And a z-score is a score that is calculated as the difference between a single raw score of 1 unit and the group from which that score was obtained, divided by the standard deviation of that sample. The z-score is a unitless value, so the units for the numerator and the denominator cancel out. And so we therefore state that the z-score is expressed in what we call, sometimes referred to as standard deviation units. And this is our equation where we have a single score of interest. We take the difference with the group average and the group standard deviation. Now, we're going to extend this into something called a one sample z-test. And because the z-test is derived from a population, what we're going to do in this example is we're going to determine if our sample is actually representative of the larger population from which that sample was obtained. And so we're going to go to our question here: if the average salary of the Toronto Raptors players are different from all NBA players. So we're going to take our z-score equation and we're going to modify it slightly. So on the left-hand side, we still have our z calculations, so we're going to calculate this. Mathematically, the equation here is identical to the z equation that we've covered previously, except that the unit of interest is no longer just one research participant, but in this case is the average of a group, the average of a sample. That sample refers to the Toronto Raptors players. And we're going to subtract the population average for average salary, and we're going to divide that by a measure of variability, and in this case it's going to be the standard deviation of that, the standard error of the mean with the z-test. So the information that we need through some research, we research the salaries of players. And when we do that, we find that of all the players on the team, the average salary of all the players for 1 year is just greater than $4.3 million per player. We find that the NBA salary average without the Toronto Raptors is over $5.1 million. So when we examine these two values here, we might look at this and say, well, the average Toronto Raptor player is paid less than the NBA average, which would be true, but in statistics and quantitative methods, we want to be assured that this difference is not we want to be assured of whether this difference is different than random chance or is truly something that is systematic with the salary structures. In order to make that determination, we have to examine the NBA salary standard deviation. So the NBA is the population, and what we find is that the standard deviation is just over $5.2 million per player. So what we see here is that we have a very large standard deviation about the average. We assume that there are 17 players per team, so that is something that's going to be necessary to carry out the one sample z-test. To begin this process, we always start with a statement of the null hypothesis. And this statement is stating that the difference in the Toronto Raptors salary from the NBA is not going to be different. It's going to be the same. So the mu is going to be equal to the population value of 5.193 million. The alternative is stating that it's not going to be different than the population average. And so what we're examining here is if the Toronto Raptors average salary is going to be different than the population. So carrying through with our one sample z-test, we have our information in terms of the average salary of the Raptors, the population average, the population standard deviation, the number of players on the team. And so we use the prescribed equation that we see for the one sample z-test. So we look at our data, we examine our data, we look at what needs to be substituted. And so we go through, we find the average salary for the Toronto Raptors. It's over $4.3 million. We put that in here. 4,392,000. This should be a comma. Subtract the difference, or subtract the average NBA salary. But notice our denominator, we still have our symbol. So we need to calculate this value from the standard deviation and the number of players per team. And so this is a formula we saw a little bit earlier, where we take that standard deviation and we divide it by the square root of the sample size. And the sample size is 17 players per team. And we get the standard error of the mean for this population to be over $1.2 million. When we substitute those values and we work through our calculation, know that the units are in dollars. Because we have dollars in the numerator, dollars in the denominator, those units cancel, and we have a unitless value of negative 0.63. So to examine this in terms of its location, we go to the normal curve, the normal distribution, and we're making an assumption that the data, the real data that we examine, is going to be reflective of the normal distribution. So we have our 95% non-critical region. And so the 95% non-critical region in the normal distribution is bounded by a z-value of positive 1.96 and negative 1.96, not quite 2 standard deviations. And so the non-critical region refers to that region that captures 95% of the entire population. We want to be assured that the difference, if there is a difference between the Raptors salary and the NBA average, that is beyond the shadow of a doubt with respect to the risk of a 5% mistake. And so what we want to examine is whether that calculated z-value resides somewhere in the critical region. And so in this example, we have 2 critical regions. We have one on the low end, one on the high end. And because the entire area captures 100%, and we subtract that from the 95% bounded by 1.96, then we're left with 5% that we split in half to the lower side, in this case on the z-scale, to the negative side, and to the positive side. And so we asked this question that we posed before, and what is a z-value of plus minus 1.96? It's almost 2 standard deviation units, and it captures 95% of all the scores within this distribution. So if we find our calculated z-value falls between positive and negative 1.96, then we do not reject the null hypothesis. Recall that the null hypothesis stated that there would be no statistical difference between the Raptors' average salary per player and the NBA average. However, if the calculated z-value exceeds positive 1.96 or exceeds negative 1.96 in the negative direction, then we would conclude at the 95% confidence level that the salary is significantly different. Now, in our case, we calculated a z-value of negative 0.63. It's negative, indicating that the value is less than the NBA average, but not to the point where it exceeded the level to which we established criticality or the significance level, which was at the 5% level. And so in terms of the Toronto Raptors average salary per player, we would conclude that the null hypothesis is true because this is where negative 0.63 resides, and thereby stating that the average Toronto Raptors player salary is not significantly different than the NBA average, because we do have to take into consideration the variability instead of just looking at the average values. And that's where our value for negative 0.63 resides. Going back to a very earlier example in terms of consuming more protein and whether it leads to bigger muscles, what we see here are a couple of regions where there is the graph clearly indicates that there's going to be this nonlinear increase in the y variable as a function of the x variable. But the symbols here on the graph, C and C, suggest, because the same letters are used, suggests that, or indicates that these two levels are not significantly different for the values on the y-axis. Likewise, the values between these 2 points are also not considered to be statistically different. And so when we look at the y-axis, as a reminder, this is our dependent variable. So this is the measure of protein synthesis, the rate of muscle growth that is going to be dependent on the value of how much protein people ingest, the independent variable. And what we see here is that when a person consumes 0 protein, that's going to be significantly lower than the B label here. So we see an increase here. We see a further increase, but statistically, when the authors went through those statistical procedures, found that 5 grams and 10 grams were not significantly different. However, 10 grams was found to be significantly different than 20 grams because of the different labels. So as a summary, in terms of hypothesis testing, for the remainder of the statistical tests that we'll perform throughout the remaining units, is that we always start with a statement of the null hypothesis in symbol and in words. Then we state the alternative hypothesis in symbol and words. And so the words would just be a one-sentence, brief sentence stating that the null hypothesis states that there is no difference between these two populations. We choose the alpha level, which is most often going to be 95, or I'm sorry, it's always going to be 5% through most of our examples. And we select one or two-tailed depending upon if our alternative hypothesis is directional or non-directional. We have not done this in this unit, but we will demonstrate how to state the rejection and the retain rule. We'll go through the actual statistical calculations, and then based upon the final answer, we will go back to our null hypothesis. We'll make a decision on whether we reject or retain the null hypothesis, and then we write the conclusion in the context of the original research question. So this ends our final lecture of Unit 3.